Hi gang, today we're going to start talking about what we call the Big Three. The Big Three are simply a set of equations that help us solve for problems where there's acceleration involved. The first of the Big Three is the equation that you derived during the free fall lab. We can solve problems like the one on the board. Seth starts from rest at the end of his driveway and accelerates down the road at 0.5 meters per second squared for 12 seconds. What is his speed at the end of 12 seconds? Well, the first of the Big Three that we derived was the equation VF equals VI plus AT. Remember, we found this by using slope-intercept form and the graph we created with the textbook while it was in free fall. So to solve any of these problems while using the Big Three or for accelerated motion, we're going to set up what we call a kinematics chart. That looks like this: X, VI, VF, A, and T. You've seen something like this before. The next step is to fill in the variables that we know. So if we go through our problem again and circle the numbers, 12 seconds, 0.5 meters per second squared, we can fill those in our chart. 0.5 meters per second squared is an acceleration, so I'm going to put that in for A. And then 12 seconds is a measurement of time, so that's T. Now, in order to solve for any of the equations in the Big Three, including the one on the board, we must have 3 of the 5 variables in our chart. Right now, we only have 2, which means we must be missing something. So what are some hidden givens that are provided in this problem? Well, it says that Seth starts from rest. We know that this means that Seth did not move at first, and then he started to accelerate. So his initial velocity was actually 0. Now that we have 3 things, we can use our equation to solve for the other 2. In this particular problem, we're looking for final velocity. So what I'll do in my chart is I'm going to put a star next to the one I'm looking for. And I'm going to put a line through the other variable that I don't know. This will come in handy later. All right, now we substitute and solve. VF equals 0 plus 0.5 times 12. Using a calculator, I find that this means Seth's final velocity was 6 meters per second. In addition to the equation that you derived from the free fall lab, which again was final velocity equals initial velocity plus the acceleration multiplied by the time, there are 2 other Big Three equations, which are also simply derived from graphs. If you're interested, ask your teacher and he can show you how. The other 2 equations, though, look something like this. Notice that each one of these equations has acceleration in it. Again, that means that these equations are used for problems where an object is accelerating. As I'm sure you already know, but just as a reminder, here's what each of the variables in these equations mean. And remember, when solving any of the problems, 3 is key. You must have 3 variables to solve for the other 2. Let's try another problem using one of the new equations. Alright, now we're going to try a new problem using one of the new kinematics equations, or one of the Big Three. Let's pretend that we're doing the free fall lab off of a really tall building that's about 100 stories high. In fact, this building is about 400 meters tall. And we're going to start with the textbook in our hands, holding it at rest, which means its initial velocity is going to be 0. And the question at hand is going to be, how fast will the textbook be moving once it strikes the ground? I know that once it hits the ground, it's going to be 0. So what I really mean is, how fast is it moving right before it hits the ground while it's still in free fall? So to solve this problem, we're going to start with our kinematics chart. And based on the information that I've provided you, we know two things right out of the gate. That the initial velocity is 0, and that the distance, or the displacement of the textbook, is going to be 400 meters. Now, that's only two things, and remember, 3 is key. So what is one other hidden given that we might be missing? Well, this textbook is going to be in free fall, which means that its acceleration is negative 9.8 meters per second squared, because we're on Earth. Ultimately, the problem is asking us to solve for how fast. So we're looking for the final velocity. I do not know what the time is, so I'm going to put a line through the time. So now your decision is, which equation should you use? Remember, there are 3. Well, the key here is to find an equation that has Vf, because that's what you're looking for, and does not have t. If it has t in it, we're going to have 2 unknown variables and we're going to get stuck. So which equation is that? Vf squared equals Vi squared plus 2ax. So now let's substitute and solve. The reason why I just added a negative sign into the displacement is because, remember, displacement is a vector, and that means that it's traveling down. So, or at least, the reason why I added a negative sign is because the textbook is traveling down. And remember that everything in this chart is a vector, except for time. So we have to include that direction, which means this 400 meters is negative. Okay, so I'm not quite finished. Notice that this is Vf squared equals 7,840. That is really fast, and that's because we're not quite done. So what do we have to do next? Well, we have to get rid of this squared. In order to do that, we have to do the opposite operation, which is taking the square. Which leaves me with 88.5 meters per second. Because the question is asking how fast, I'll leave that as a positive number because it's just the magnitude and not the direction. If the question asks me for velocity, however, the textbook is moving down, so it should be a negative velocity. That's about it.